Now we'll go for the second part. The second part will cover the molarities, calculation of different molarities. We'll start with the first one here. Another way to express the molarity is the mass percentage, mass over volume percentage, mass and the volume percentage. So mass over the volume percentage, which is this one here, is defined as, that's the formula, and that's the unit. That's the units here. This is the unit of the solvent, and this is the overall unit of the formula. So what we are really interested in this one, this is very, very important, the formula. So mass over the volume is mass of the solute in grams, by the way, in grams, the solute in grams, and mass of the solution in milliliters. And then you multiply it by 100%. Mass over mass percentage, now we have to introduce the mass of the solvent. So mass of the same definition, mass of the solute divided by the mass of the solution. However, mass of the solution here is defined as mass of the solute plus mass of the solvent. The solute unit is grams, and the solute of the solution, which is mass of the solute plus mass of the solvent in grams, and then multiplied by 100%. The third type is volume over the volume percentage, which is the same way as the mass over mass. Here we have to do the volume of the solute in milliliters divided by the total volume of the solution. The total volume of the solution here is volume of the solute and the volume of the solvent, and the solute in milliliters, and the solution, which is the sum of the volume of the solute and the volume of the solvent in milliliters, multiplied by 100. The molarity, defined as number of moles of the solute divided by liters of the solution, again, is number of moles of the solute divided by the volume of the solution in liters. Why I'm putting emphasis on this? Because we have in the next molality. Molality is, which is here, the same definition, moles of the solute. Now we don't have the solution volume in liters, we have mass of the solvent in kilogram. So the solute units moles, the solvent in kilogram. And while if you compare it with the molarity, the solute in moles, but the volume of the solution in liters. So that's the difference between molarity and molality. Equivalent molarity of the electrolytes is equal to milliequivalents per liter of the solution. The moles of the solute is milliequivalent, MEQ, and the solution is in liter. And this is the overall units of the formula of the equivalent molarity, which is MEQ/liter. Dilution law can be written as C1V1 equals C2V2, or sometimes some textbook they like to have it M1V1 equal M2V2, because M is molarity and C is the concentration. So C1 and M1, those are the stock concentration or molarity of the solution. So that's what this dilution all about. And the concentration or the molarity in mole per liter, correct? Solute is moles, and the solution in liters, mole per liters. Let's go further and look. The last thing here, part per million ppm or part per billion ppb. And if you look at this, part per million is mass of the solute divided by mass of the solution multiplied by 10 power 6. And you know 10 power 6 is millions, correct? or called mega. So million, 10 power 6 is million. And the part per million is the same thing here, mass of the solute divided by mass of the solution and multiplied by 10 power 9, which is billions, correct? 10 power 6, or called in another prefix is giga, correct? Giga. So if you look at this is part per million and part per billion, and we'll know how to relate each other. You can see the difference between them is 1,000. So it's really is 1,000. So if you look at this as 10 power 6, 10 power 9 is 1,000, the difference between them. So let's go further, and we'll have examples of each type of molarity, concentration of formula. First, let's take an example of mass over the volume percentage. We said the formula is the mass of volume percentage, the mass of the solute in grams, correct, divided by, this is divided here, divided by volume of the solution in milliliters, mass of the solute in grams, multiplied by 100. So let's look at an example here. We have to calculate the mass over volume percentage of a solution formed by mixing, this is the amount of solute, which is sodium chloride, 25.0 grams of sodium chloride in 455 ml of H2O. Just plug in, according to the formula, 25.5, this one here, divided by the amount of the, divided by the amount of the solution, multiplied by 100. And this gives you a large number here, the calculator, and you have always, as I said, to observe significant figure. 3 sig fix, correct? And here is 3 sig fix, and the answer will be the answer is 3 sig fix, correct? The answer is 3 sig fix. So the answer is 5.5. So divide 25.0 divided by 455 multiplied by 100 give you, abbreviated to correct sig fix, rounding off 5.50, 3 sig fix. Another example. Now I will give, there will be given to us the percentage, the mass over the volume percentage of the solution, and we have to calculate the amount of the solute or the amount of the solution. Either or, the amount of solute in grams, or sometimes the amount of solution in milliliters. Now here is given to us, the percentage is given to us, and we have to calculate the number of grams of the solute in a solution made of 1,000 liter. Again, this liter, we have to convert the liter into milliliters, because by definition it has to be solution volume in milliliters. Let's set it up. The same thing, mass of the solute divided by volume of the solution multiplied by 100. This is the percentage here you have, 38.5 percentage, gram over mil percentage. X is our what? X is our unknown amount in grams of unknown mass of the solute, and divided by 1,000 milliliter, because we have to convert, we have converted our 1 milliliter, 1 liter into 1,000 milliliter. You work it out, and the X, then solve for X, correct? Yes, solve for X. And the X will be 385 gram potassium nitrate. Let's verify this. If I take this gram here, divided by 1,000, correct, multiplied by 100, it should give me 38.5, and it does. So this is correct. This is correct. Let's go further and go look at mass over mass percentage. And if you look at the formula here again, let's repeat ourselves, is mass of the solute divided by the mass of the solution. And the mass of the solution here, this is again here, that's another definition, which is mass of the solute and mass of the solvent. And now we have a solution formed by adding 48 grams of lithium sulfate to 250 grams of H2O. What is the percentage by mass of lithium sulfate? Well, we know that the solvent is this. We know the solute is this amount. All these masses, we know them. So just plugged in 48 grams of the solute divided by the sum, 48 plus of the solute plus the 250 grams of the solvent. And the whole thing multiplied by 100. And it came out to the large, large number here, 16 point whatever. That's from the calculator, rounding off to correct sig fix, which is two significant figure, which will be 16. You can verify it. Divide 16 by the sum of 48 plus 250 will give you the 16 point percentage. 16%. So further, what is the mass of the solvent H2O in grams for a solution made of? Now the solution is given to you at the percentage of it, and you add this solution of in percent of each component in the mixture formed by adding 2 grams of aluminum nitrate in H2O. So here we have 10.5%, correct? And we have here each component add into the mixture by adding 2 grams of aluminum nitrate in H2O. We don't know how much H2O is all about, correct? So let's set it up. Mass of the solution, mass of the solute, again, mass of the solute and mass of the solvent, both. Mass of the whole solution, we don't know, we can put it X. Okay? So 10.5% over 100, that's the percentage, equal 2 gram aluminum nitrate divided by X, which is the grams of the solution. So solve it for X, X will be 19.0. If X 19.0, then H2, and we have aluminum is 2.0, then the amount of the solvent H2O is 19 minus 2.0 is 17.0 gram of H2O. You can verify it. Take your 2.00 gram divided by the sum of the 17 plus 2, which is 19, correct? And it will come exactly 10.5%. So the answer is here, after verification, is correct. So let's go another example. Now we'll go volume to volume. It's the same like the mass over the mass. We have to just here to take in consideration the sum of the total volume, which is volume of the solute plus volume of the solvent. So let's look at this example. What is the percentage percent by volume of a solution formed by adding 25 liter of ethanol to 155 liter of H2O? Well, straightforward. We have the solute is a small amount, which is ethanol, correct? So take this, this is your 25 liter. And here is the sum of both, 25 plus 155, correct? So 25 plus, that will be 25 divided by 180. The sum of 155 plus 25 is 180. Multiply by 100, I give you this large number here. We have to round it off to the correct sig fix, which is 2 sig fix. Here is 2, correct? The least. So 2 sig fix, which is 14%, and you can verify it as well. So milliliter over milliliter percentage. So take this of the solute divided by the sum, 180 multiplied by 100, it will give you the same 14%. Okay, let's go and look at another example here. The example here is we have the percentage, volume percentage is given to you, 5.50. And the amount of the volume of the solute, acetone is the solute, and H2O is the solvent. Calculate the amount of the acetone in milliliter added. Now, if you look at this, we don't know what's the solute amount, correct? In volume, the volume of the solute, we don't know. So we assume the solute is X. So 5.50, which is 5.50 divided by 100, which came out to this value. The amount of the solute, the amount means the volume of the solute, we don't know, X, divided by the total volume of the solution, which is the solute plus the solvent. So X plus 255 ml. Work it out. That's just simple working out for X. So X then will come to be 14.8 mLs, rounding it to 3 sig figs. Correct? And you can verify this if this is really true. So the amount of the acetone solute is 14.8 mLs. Take 14.8 mLs in the top as a solute divided by the total. Correct? Total will be 14.8 plus 255, and the whole thing multiplied by 100, you get 5.50, and which is the correct answer. Now let's go for the molarity. Molarity is moles of the solute divided by liters of the solution. The direct question is, calculate the molarity of a solution made by dissolving 35.0 gram of sodium chloride, that's the solute, in 97,890 milliliter distilled H2O. So this is your solvent, correct? Or the solution. So now we need, in order to get this, we have to get the moles, because by definition moles. How you get the grams? From the grams you get the moles, you have to go through what? The molar mass. So first let's calculate the molar mass of sodium chloride, which is the sum of atomic masses of sodium and chlorine. And it came out to be here, 23.0 for sodium, gram per mole, 35.5 gram per mole for chlorine, and the sum of both 58.5 gram per mole. Now we calculate number of moles of sodium chloride. We take the 35.5 grams, correct? Here it is, and you divide it by the molar mass. We have to divide by the molar mass. Yeah. We have to divide by the molar mass. So, and the answer is number of moles. Now we have in milliliters, so we have to convert this milliliters into liter by dividing by 1,000. Correct. So dividing this by 1,000, we get our liters. So moles of sodium chloride divided by liter of the solution, and we get to round to 3 sig figs, we get the value of 0.00611 mole per liter. Please note that this molarity can be written in 3 different ways. Mole per liter as a unit, capital M, or molar. So we have 3 molar, so the same value, capital M, or mole per liter. So three ways to write or to express the molarity unit: mole per liter, capital M, or molar. Let's go further here. Now I can give you the desired molarity, and I want to prepare this one in the lab. I want to prepare 2.675 molarity by dissolving 8.50 grams of magnesium nitrate in certain amount of distilled H2O. Calculate that desired H2O. We have to add to the 8.50 grams to produce 2.675 molar. Those type of questions are faced to the students during the lab sessions. So it's straightforward. You know that M is mole per liter, correct? So, and this is, you have the grams. You have first, we have to go through what? Magnesium nitrate, we have to go through its molar mass. So that is very important. Molar mass of magnesium nitrate: 1 magnesium, 2 nitrogen, and 6 oxygens. Correct? So you can look, 6 oxygen, 2 nitrogens, and 1 magnesium, and it came out to be 148.3 gram per mole magnesium nitrate. So we have the mole, so we have the gram, we have the molar mass, we have the grams. We can calculate what? The moles. So the moles of magnesium, straightforward. So will be the number of grams divided by molar mass. This is the the mass of the solute, you divide it by the molar mass, you get number of moles, and this is the moles here, correct? So now you have the moles. You know, if you have 8.50 grams, that is equal to 0.0573 moles. But the desired molarity is 2.675 mole per liter. So if you have this, so what you will do here, you will take the moles you have calculated, correct? You divide it by x. Here x is your liter, but here is 2.675 mole per liter, correct? So now you can just the easiest way to do is to take your moles here and you divide it by the molarity to get the amount of liters. So take this, you divide it, that's your x, and divide it by the molarity to get the liters, and the liters are here 0.2014. You can verify this. If you take this number of moles, you divide by liters, you should have the same desired molarity started in the question itself. Okay, so let's go further. Now, suppose in some areas, you will not get number of moles direct. Indirect, you have to calculate the number of moles. So suppose you get number of molecules of the solute, number of molecules, dissolved to make 3,500 milliliter of H2O solvent, correct? That's acetone dissolved in 3,500 milliliter, which is 3.500 liter. Calculate the molarity of acetone. Well, here we have to use Avogadros. We need really Avogadros to help us to get these molecules out of the way. We are not interested in molecules. We are interested in moles, and we, as you recall, 1 mole of the matter, or 1 mole of 1 mole is equal by definition Avogadro's number of molecules, or Avogadro's number of atoms, or Avogadro's number of ions, or formula units, sometimes called. Okay, so the number of moles of acetone, we take the number of molecules given to us, correct? Number of molecules, and then you multiply it by Avogadro's number. So you can see the molecules with the molecules cancels out, and you end up with the value of the moles is 1,660 moles, correct? And the volume has to be converted into liters. It's 3.500 liter. So then you divide the number of moles. Here you have the number of moles divided by the number of the liters. You end up with rounding off. You end up with the answer is 4 sig figs, 474.5 molar. Okay. Molality now. Molality is the same, similar to molarity, but now we don't deal with the liters. We don't deal the volumes in liters, but we deal with kilogram of the solvent. We deal with the kilogram of the solvent. Let's look at one of the examples here. What is the molarity of solution made of gram of aluminum nitrate? Here it is. When dissolved in 5,500 gram of H2O. Well, first you need the molar mass. Again, we are repeating ourselves always. In order to get the moles, you have to go through the molar mass, or sometimes through Avogadro's number. So, but most of the time we are dealing with the molar mass. So let's calculate the molar mass of aluminum nitrate. 1 aluminum, 3 nitrogen, and 9 oxygen. So aluminum is 27.0 gram per mole atomic mass. Nitrogen is 14.0 multiplied by 3 of them. And 9 oxygen is 16. 9 multiplied by 16, it ends up with the molar mass of the aluminum nitrate is 213.0 gram per mole. Number of moles, then you can see now we have the molar mass and we have the mass, correct? So what you'll take the mass, You divided, take the mass you have given here, and what you will do here, this is the molar mass, correct? And this is the mass. You take the mass divided by the molar mass to get your moles, correct? So take the amount of whatever you have, 9.38 grams of aluminum, the mass divided by the molar mass, correct? To get the nitrate number of moles. And then this is the solute moles. The solvent, you have to get out 5,500 grams into kilograms, converted by dividing by 1,000. And then at the end, take the number of moles you have divided by the kilogram H2O. You get your molarity. Rounding it to the correct sig fix, you end up with 0.0081 mole per kilogram. Now, here we have the same, similar to the molarity. We have three types of units can be written the molarity, like the molarity. So the first one is mole per kilogram, the molarity mole per liter, correct? And the capital M, that's molarity. Small m is molality. Or in molarity, we kept molar with R. Here is molal with L at the end. Molarity with R at the end, here is with L at the end. So now let's look at this one here. What mass of H2O is required to dissolve 45 grams of calcium chloride to prepare 2.50? Small m is molal, correct? So you have the molality here, which is 250, correct, moles per kilogram. And we need to get the mass of H2O. So, well, you just you get the grams of calcium chloride. So you need to convert again. Get the molar mass of calcium chloride. This is the molar mass of calcium chloride. Here we have it. See here. We have calcium chloride, 1 calcium, 2 chlorine. Calcium is 40.00 gram per mole. The chlorine is 35.5 gram per mole. You add them up, 100, and this is 111 gram per mole. Take this 45 grams of calcium divided by its molar mass. So you divide it by this, by the molar mass, to get number of moles. This is the number of moles of your molality 2.50. Set them up, equalize them. The 2.50 molar is 2.5 calcium chloride mole per kilogram H2O, correct? Which is equal to 0.405 moles divided by X. Calculate the whole thing and you'll end up X here equal to 0.16 kilogram H2O. You can verify this by taking the number of moles here you have divided by the kilogram, and you should get 2.50 mole. So let's go further here. The equivalent molarity of the electrolytes. Well, the equivalent molarity of the electrolytes is very unique, especially in electrochemistry. Milli equivalent calculations come in 3 topics, and we can cover one example at the time. First of all, converting milli equivalent to weight. Converting weight to milli equivalent, that's the opposite direction. And then converting milligrams percentage into milli equivalent. So those are the 3 areas that we are dealing with milli equivalents. Although nowadays is more or less the mole calculations is overseeing this, because we can say calcium chloride, for example, it has 1 mole of calcium and 2 moles of chloride. Or you can say 1 milli equivalent of calcium, calcium has 2 milli equivalent, 2 equivalent, and chlorine has one negative charge has 1 equivalent. So whatever charge the ion does carry, that will be the equivalent. So it depends on the charge that the ion is carrying. So For example, sodium is carrying positive 1, so the equivalent is 1 mole of an ionic compound, is 1 mole. So sodium chloride dissolved in H2O will produce 1 mole of sodium plus and 1 mole of chloride. So each one is equal to 1 equivalent. So it will produce 1 equivalent sodium and 1 equivalent chloride, sodium ion and 1 equivalent chloride ion. So here's the table, shows you. Those are the ions. All of them is positive 1, positive 1. Oxidation number is +1. And the number of the equivalent per mole of course, make sure that you understand, that's per mole. This is 1. Those are number charges 2, ion charges 2 here, and the oxidation number +2, and this is 2 equivalent per mole, and so on. We come to the polyatomic ions. Carbon is 2 negative, ion charge is -2, the ion oxidation number -2, with the same thing with the sulfate, and we are dealing with 2 equivalent. Whatever charge they are carrying, whatever the polyatomic ion or the ion itself, it does not matter if it's positive or negative, but it does the amount. So phosphate has 3 negative. We are looking at the 3. So the 3 will be 3 equivalent per 1 mole. Let's look at some examples here so we can go and look at the conversion. So what is the concentration of a solution contains 8.50 milliequivalent per liter of sodium chloride? What is the concentration of the solution contains 8.50 milliequivalent per liter of sodium chloride? First, the molar mass of sodium chloride, correct? Because we need the moles, correct? So we have to get anything through the molar mass. So to get the moles. The molar mass, sodium chloride, we did, sodium is 23, chlorine is 35.5, makes 58 gram per mole. That's the molar mass of sodium chloride, correct? Now, we use the general formula, and this is the general formula here. Look at the general formula here. Here it is. Milligram, that's not magnesium, that's milligram. Milligram per liter equal to milliequivalent per liter. Milligram is milliequivalent per liter, multiplied by atomic mass or molar mass. In this case, we have molar mass. And this is by itself here. This is by itself divided by number of the equivalents, correct? Number of the equivalents. So let's look at this. So I have 8.50 milliequivalent, correct? And then multiply by the molar mass. This is the molar mass, and this is number of the milliequivalent. So this is the first one, correct? And 1 equivalent per 1 mole, correct? For the whole molecule, sodium is 1 and chlorine is 1. 1 equivalent per 1 mole, it give you this amount, correct? So, and we round the whole thing to 3 significant figure. Is 4.97, is 4.2 decimal, and then 2.5. We take the 2.5 out, and this will be 3 significant figure. So let's go here further. Converting weight to milliequivalent. Again here, how many milliequivalent of sodium chloride in 10.0 gram of sodium chloride? Again, you need the molar mass sodium chloride, which is this one here, and you use the same stuff here before we did. Milliequivalent is whatever is number of grams, in this case, of sodium, but in this case the opposite was whatever we have before, correct? If you look here the milligram per liter, correct? We have to multiply the milliequivalent multiplied by atomic mass divided by number of the equivalent. Here we have the number of grams is given to us. I divided by the molar mass to get number of moles. So here it is. This is to get number of moles. And then I multiply here. Look at this. I multiply by equivalent per 1 mole. Multiply. Correct? So I have this is by itself. sorry, but this is by itself here, divided by the molar mass, correct? And the molar mass is multiplied by all those three. Here it is. So if I look at this, milli equivalent is 10.5 grams of sodium chloride divided by the multiplication of the molar mass, correct? Multiplied by the equivalent per 1 mole, multiplied by 1000 milli equivalent per 1 equivalent, will give me 179 milli equivalent. So you have to divide the mass over the whole thing, over the molar mass, because they'll give you the number of moles, and then you get number of moles, you'll multiply it by equivalent per mole. The mole cancels out with the mole of the molar mass, and then the equivalent will convert it into milli equivalent by multiplying it by 1000 to get milli equivalent. Converting milligrams into milli equivalent. Well, let's convert percentage, of course, milligram percentage. So let's convert this one here into of barium 2 plus into milli equivalent per liter. So the atomic mass of the barium is 137.3. This is because we have to go through mole. We have to go through the mole. That's the main important stuff in this equivalent, is number of mole. And therefore some textbook, they don't really cover it that much, because the modern calculation, you don't need the equivalent. You just calculate the whole thing based on the mole, and you get to you end up with the same results. So barium has 2 plus ion, and the 2 equivalent is 2 plus, correct? So now equivalent mass of barium is, the equivalent mass of the barium is, this is the atomic mass, divided, the same thing we did before. The same as just here. Here is, we took the mass divided by the molar mass and the whole thing here, correct? And here we take the molar mass, you divide it by how many equivalent of barium? 2, divided by 2. So I get here, this is, correct, gram, because that's the mole here, sorry, the mole here cancels with the mole. So this is gram per equivalent, correct? Now, I come here, 1 milli equivalent, so I have to convert this equivalent to the gram into milligram by dividing it by 1000. So by multiplying by 1000. So the gram will be converted into to milligram. You multiply it by 1000 to get how many milligrams, correct? So then you have the percentage, 15%, correct? 15% milligram will be the 15.0 milligram of barium divided by 100 mL of the solvent, correct? Because this is a percentage, means 15 divided by 100, correct? And this one will be 100 multiplied by 1000 will give you 150 milligram per liter. And then we have this one here. Look at this. We have to use it. 0.687 milligram per 1 milli equivalent is equal to 150 milligram over X milli equivalent, correct? So, and then solve for X, because 0.0687 milligram per 1 milli equivalent, which is we did here. So we transferred this one here into milligram. So here is transferred into milligram. So this is transferred into milligram, and therefore you can see, solve for X. X is here is the number of X is rounded off to 2180 milli equivalent per liter, which is turned out to be 2.18 10 power 3 milli equivalent per liter. Okay, dilution. dilution, we said that C for concentration, M for molarity. And we always take from the stock solution, the first one here, the stock solution, the more concentrated. And this is the same thing, the more concentrated. And here is the least or the diluted one. And this is the law of dilution. So let's look at some of the example we have here. Let's look at the first example here. If I have 75.5 mL of H2O added to this solution made of this. So I have a solution which has the molarity of this, and this is the amount of it available, correct? And this will be my stock. This is the concentrated one. And then I add to it H2O, I dilute it, I make its concentration less, correct? So I'll put this one here. Those are, multiply those together, C1, V1, equals C2, I don't know what the concentration of the diluted solution is. I know it's volume. So just I put everything together here, but the volume here, watch out for the volume. Here we have to use the total volume because you add the 75.5 to 875 milliliters. So you have to have the V2 here. The V2 is the sum of both volume, the total volume, correct, of the solution. When you add the 75.5 to 875, now that's the total volume will be considered. So then 0.125 molar multiplied by 875 milliliter equals C1 or C2 multiplied by the total volume 950.5 milliliter. You solve it, and here we have the 0.115 molar. With those type of calculations, you have to watch, because we are talking about dilution. This has to be the diluted one, and your answer, if you make an error, then you can just look at the inspect your values, the answers. The answer has to be less, very diluted, less. 0.115 is least or is less than 0.125. Therefore, my calculation has to be correct. But if I get more than whatever I started with, then there is an error somewhere. So let's look at another example. I have here 500 mL added to 0.15 molar HCl solution, correct? Till the total volume is, this is the total volume, 650. What will be the molarity of the diluted solution? Well, C1, the concentration of the concentrated one, the stock solution called, C1 multiplied by V1 equals C2 multiplied by V2. We don't know what C2 is, but we know the V2 is here. This is our V2 here, correct? This is V2. And this is my C1, correct? If I look at this, this is my C1. And this one here, my V1. Just set it up, correct? Set it up here, see here. Set it up here and divide it by the, calculate the C2, and you get the answer is 0.115 molar. Let's go for C. This is B, this is C. How much H2O should be added to 985 ml of 6.55 sodium hydroxide to make 1.5 molar solution? Remember now, you are going from the concentrated to the diluted, correct? And you added H2O to that. So you have to add total. So 985, this is just the concentrated solution of this. Then the total volume will be X plus 985. And you have to calculate the X, which is the amount of H2O, correct? So let's calculate this. You have 6.55 molar, the concentrated one, stock solution, multiplied by its volume, 955 ml. You produce 1.05 ml multiplied by V2, correct? Get your V2. The V2 came out to be 6,451.75 ml. Now this one here, you know that this is the sum of both. The sum of 955 plus H2O. So subtract the 6,451.75 ml minus 985. That will give you then the value of X will be your 5,466. 5,466 rounded off to three significant figure will be 5,470 rounded to three sig figs. D, we have 450.5 mL of 2.66 molar potassium nitrate solution. If one boils, now the keyword boils, if you boil a solution, you make it diluted or concentrated? You make it concentrated because you get rid of some of the solvent there, correct? So we are expecting our value will be larger than 2.66 we started with, correct? So let's boil, and then after this, you boil it until the volume of the solution is half of its what started with. What will be the molarity of the solution after boiling? This is very important. This is boiling means it has to be more. It will be more concentrated, not diluted. We are concentrating, not diluting. So the total volume here, again, you have to look at the total volume. So total volume is V2. We know the C1, V1 is given to us, 2.660 multiplied by 450.5 ml. The V2 we don't know. This is the V2 will be, we know V2. V2 will be 455 divided by 2, which is 225. Half of it. It said half. So it will be 225.53. So now let's calculate this. C2 will be this one here. This together here. C1, V1. You started with stock solution. And then you boil it to the half, you divide it by the half, you divide it by this, and guess what? You get 5.319. So almost what? Almost double the concentration, double the molarity when you boil. So that's what boiling of stock solution had led to higher concentration of new boiled solution. So almost double the molarity. Part per million and part per billion. Part per million is just you take part of million, take 1,000 part of 1,000 parts of per billion, correct? And that's the way we can transfer each one of those here. So what is part per million? Is mass of the solute divided by mass of the solution, multiply by 10 power 6. Part per million, mass of the solute, same thing here, divided by mass of the solution, multiplied by 10 power 9. 10 power 6 is million, 10 power 9 is billion, correct? Or another prefix, this is mega and this is giga. So mega or giga. So example. Solubility of sodium chloride is 284 grams per 100 gram of H2O. What is the concentration in ppm? Remember, 285 grams, you divide it by the total, the sample, the mass of the sample, you multiply it by 6. By, 6 zeros by 10 power 6, sorry, by 10 power 6. Correct? And if you make it like this, so the 2 zeros out, you'll end up having 284,000 part per million. So just mass of the solute divided by mass of the solution multiplied by 10 power 6. That will give you part per million. Multiplied by 10 power 9 will give you part per billion. Here is another example. The solubility of silver chloride is this, 0.008 grams per 100 gram of H2O. How we can express this one in part per million? Straightforward. 0.008 grams correct? Divide by 100 grams, grams cancels out, multiply by the 6, 1, 2, 3, 4, 5, 6, correct? The two zeros here cancels with the two zeros. Here's the two zeros will cancel out to the zeros, correct? So it will be 80, yeah, will be 80 parts per million, correct? Yeah. So the certain pesticide has a toxicity, toxic solubility of 5 grams to kilogram body weight. What is the solubility in part per million? Take the grams first, the kilograms in 1 gram, kilogram 1000 grams, so 5.0 grams. Take this, divided by 1000 gram, this is 1 kilogram, multiplied by power 6, correct? And 3 cancels out, 3 zeros cancels out, you get 500 parts per million. So here it is, convert 50 parts per million into convert 50 parts per million into part per million. Well, it turns out part per million is 1 part per million over 1000, or it looks like, you know, it looks like 1 part per million is 1000 parts per million, correct? So if you look like this, 50 parts per million is equal to, so 50 parts per million equal 50,000 parts per billion. 50 parts per, yeah. The part per million will be 50 parts per million. So, let's look at this. How many grams in 1 milligram per liter? By definition, is 1 milligram liter is 1 gram. 1 milligram per liter is 1 ppm by definition. So let's go further. Look, we want to see the concentration calculations in chemical reactions. This is the real, they call it stoichiometry in chemical reaction, and this is really is all about first balancing chemical equations. You have to start with the balanced chemical equation. After balancing chemical equation, you have to look at the ratio between the reactants and the products, or among the reactants themselves, or among the product themselves. Use this ratio with the help of the molar mass of the desired or asked reactant or product. You can calculate the number of grams or whatever, or molarity or anything asked for that. But those are the steps. Are the steps. It says if 355 mils of 0.380 molar sodium phosphate, this is for sodium phosphate, react with calcium nitrate at this double displacement, produce a precipitate solid calcium phosphate and aqueous sodium nitrate. So now I have to watch for the mole ratio. This is 2 here. Let me just, this is 2 here. This is 3 here. This is 1 here. It's not written, but understood is 1. This is 6. So I have to watch for those mole ratio. So now it gives me the molarity of sodium phosphate. Correct? If this is 355 mils of sodium phosphate needed to react with 0.15 calcium nitrate, calculate the amount of the volume of calcium nitrate needed for this reaction. From this, what we can see, we are setting this but with the steps. The first step, number of moles given reactant using its molarity and volume. So the moles of sodium phosphate will come from the multiplication of the molarity of sodium phosphate with liters. We have to convert this into liters of the volume of sodium phosphate. So first of all, we calculate the number of moles of the given reactant, sodium phosphate. So this multiplied by the 3.355.0 milliliters has to be converted into liters, multiply by mole per liter, 0.380. So then you get number of moles, which is turned to be this amount here, moles of sodium phosphate. Then step 2 here, using those mole ratio, then we can go to there and we say, well, I have 2 moles of sodium phosphate will always react with 3 moles of calcium nitrate, or I have 3 calcium nitrate will react with 2 moles of sodium phosphate. So I set it up here. Look at this, 2 moles of sodium phosphate divided by 3 moles of, that's the ratio, 3 moles of calcium nitrate, or 3 moles of calcium nitrate to 2 moles of sodium phosphate here, correct? So here it is, of calcium phosphate here. So next step here, to calculate number of moles of calcium nitrate, correct? We have to calculate, we know the number of moles of sodium phosphate by multiply the volume in liters by its molarity. You get number of moles of potassium, sodium phosphate. We have to get calcium nitrate by setting this up. So next step is, look at this, I have moles of calcium nitrate will be 3 moles of calcium nitrate divided by 2 moles of sodium phosphate multiplied by number of moles of sodium phosphate. So the mole of sodium phosphate will cancels out with the moles of calcium phosphate. So 3/2 multiplied by the moles of sodium phosphate will give us moles of what? Of calcium nitrate. Now, the amount of the volume, we have the calcium nitrate moles, and we have what? We know the molarity of calcium nitrate, correct? Do we know the calcium nitrate molarity? Yes, this is here, 1.135. So what I will do here, I divide whatever number of moles of calcium nitrate by its molarity. Here it is, divide by its molarity here, which is this 0.135, I get 1.50 liter, 3 sig figs, the answer. Okay, this is another example. How many liters of the hydrochloric acid would be required to react completely with 2.85 grams of sodium hydroxide, correct? According to the reaction, you can see 1 mole of HCl react with 1 mole of sodium hydroxide, 1-to-1 mole ratio. Now, if I get the grams, the molarity calculations, I have to get rid of the grams. It will not help me. I have to go to what? Moles to mole ratio, because in the equation, there's no gram to gram, it's mole to mole. So then I have to get the grams of sodium hydroxide converted into moles of sodium hydroxide. I have to calculate the molar mass of sodium hydroxide. Sodium is 23 gram per mole and oxygen is 16, correct? So if you add, the hydrogen is 1, so if you add it up, it will be 40 gram per mole, correct? Now I have, this is the molar mass. If I have the molar mass, I have to divide the number of grams by the molar mass to get number of moles. This number of moles of sodium hydroxide, because of the 1-to-1 mole ratio, correct? Look at this nicely. Because of the fact this is 1-to-1 mole ratio, this is HCl moles will equal sodium hydroxide moles, which is 0.07125 moles. If I know now the moles, correct, I know the molarity of hydrochloric acid, I can get the volume of hydrochloric acid by, look at this, divide the moles I calculated for sodium hydroxide, which is the same thing for HCl. You divide it by the molarity of HCl, and you get the value, the liters of HCl. Thank you very much. for listening.